Okay. Uh, yeah, last time we stopped short of actually defining reactants. And okay, your IFT is a cosine of omega t, then let it be IDC. The IDT is negative omega a cosine omega t, so L the IDT is negative L omega times a sine omega t. Now, this is similar. To this. Now, why do I do this? That's the voltage across the inductor. This is voltage across resistor. And we see that they're out of phase by 90 degrees. Sine is 90 degrees in rotation. Okay. You know, I probably should have done this in terms of. Well, if I've done it. With this one. Probably should have started with Q. I don't want to start with current, because that's kind of where we start when we do the phase. Sorry. Okay, so we can integrate I with respect to T. And what do we get? When we integrate I with respect to T, we get one over omega. Multiplied by a sine of omega t. That's 90 degrees out of phase with cosine in the other direction. Okay. And Q over C is 1 over omega c. Times a sine of omega t. Okay. Now, a sine of omega t has the same amplitude as a cosine of omega t, it's just out of phase. And if you get a negative sign, well, it's out of phase too. It's 180 degrees out of phase with this. 90, yeah, 90 degrees out of phase with this. Focus. Okay. Here we multiply our I cosine omega t function by R. you get voltage drop. Here we multiply by 1 over omega C, you get voltage drop. Here we multiply by negative L omega, you get voltage drop. Well, for reasons that we talked about, for high frequency circuit, omega is large. The thing we multiply by the A sine of omega t, get the charge, is going to be small. Okay. Omega c is high, this is small. So it's like the thing has a small resistance, but it's not really a resistance. Okay, it's a reactance. It acts like a resistance. And it doesn't suppress a high frequency circuit. Not from what we observed, we know that if you charge a capacitor long enough, it's going to eventually stop the current. Okay, so if we have a low frequency, we have a low value of omega c, combination of low frequency, low capacitance. That we're going to tend to block. Okay. We're going to get a lot of voltage drop, in other words, across the capacitor. For an inductor, if we have a high frequency, that means we're trying to change the current quickly in that coil. Think of a coil, okay? Which is going to induce a big magnetic field in the coil that fights it. So a high value of omega L is going to correspond to a suppression of the signal. Okay. So that defines our reactance. So this is our voltage across the inductor. This is our voltage across the resistor. This is our voltage across the capacitor. And the total voltage drop is LVL plus VR plus VC equals, we could write it as L di dt plus RI plus Q over C. Writing it with one variable function. It's L times the second derivative of Q with respect to T. Plus R dQ dt. Plus Q over C. Okay. And that's how this LRC series combination behaves. It tells you how it behaves in the circuit. We have the phasor diagram. We draw it in a big example. Okay, so if this is our current, of course, we have the circular model. As omega changes, that moves the whole thing around the circuit. And I get the frequency omega. We're going to have VL here. Okay. Now, this picture that I drew. How does the capacitive reactance compare to the inductive reactance according to this picture? Don't want to spend too much more time on this, but according to this picture, this vector is longer than this vector, which means the amplitude of the current through the capacitor is going to be greater than the amplitude of the current through the inductor and the amplitude of the voltage. Okay. And what determines the amplitude, the relative amplitude of these two things? All three things are multiplied by a times either a sine or cosine of omega t, maybe plus, maybe minus. Say that's going to give this factor the same amplitude as this one. It's the same amplitude as this one. They're just out of phase. Okay, I'm just talking about the a sine omega t, a cosine omega t, a sine omega t here. Negative there, doesn't matter. The amplitude is still going to be the same. Sine or cosine or negative sine is what's the push it, what causes these to be in different directions. Okay, cause them to be 90 degrees out of phase with one another. What determines the length of this vector is the number in front. Length of this vector is determined by 1 over omega c. Length of this one is determined by negative L omega, and the length of this one is determined by R. And you put any L, R, and C in your circuit, and they're going to behave differently for it. Which you do, okay? So you put a small capacitor and have a small angular velocity. It's going to make this big. Okay. And a big angular, I said angular velocity, angular frequency, right? Big angular frequency. Sorry, small angular frequency combined with small inductance is going to give you shorter vector. The reason all that up right there is the whole picture. And of course, the differential equations are difficult to solve. That's really bottom line, and that's kind of what I wanted to say about reactants and stuff. Again, if you're going into mechanical engineering, you want to think about the mechanical analogs. Okay. If you want to talk about that, we can. We can even talk about it a little bit in lab, but I want to review the content. Just a quick comments, and y'all are dealing with Stokes theorem and the divergence theorem, just a connection with the monotonic calculus. You got a loop around a wire. Ampere's law says you integrate around that loop. Okay, it's equal to the change in flux. Okay, and that's an analog of Stokes' law. Okay. You got kind of a flux through the thing, but it's like the flux. And integrate around the loop, and you get all that stuff. So it's just, I'm not going to make that real explicit because Stokes' theorem is not part of this course. And in that course, we have people who are not taking the figures. Yeah. So we can't really talk about it either, of course. Just a quick mention, just a concept. You might want to think about connecting more for your benefit in that course into this one. If you're going into electrical engineering, it's not an absolute law, basically. Right. Depends what electrical engineering you go into. My grandson studied power systems engineering. And yeah, they talk about Maxwell's equations that are used from some, but they didn't go into too much depth. Probably no more than the modern public calculus. Okay. Okay. So just advice for the future. Okay, so again, let's just kind of review. I kind of want to talk about how energy faces through various systems. If you have the electric field, we've got 2 points there. And then peak bill and look where to be. And for every increment on the path, we're going to have sample point, and you've got an electric field inside. Okay. Take E, and you take the delta F. If you've got a charge here, you're going to get a force. Okay. So let's let a charge you move along with that. Then there's a force. Force is in the direction along the line of E. It might be in the direction of E or opposite the direction. There's the force. There's the work. Lucky the delta there because it's the work on an increment, but that's not a totally good notation. Still using it. Okay. The contribution to the work, and we'll maybe call that W sub I. Maybe this is the I symbol, right? So okay, we got a E sub I, we got an F sub I, we got a delta F sub I. Context of it. Okay. So what's the work? What's the expression for the work? Okay, now I just wanted to stop for a second and ask, what's the work? And the answer I got, well, 4 times, the F sub I times delta S sub I. Well, it's kind of the right direction, but that's not how to calculate work factor. Okay, it's on. Because the vectors are not in the same direction. So F sub I dot delta S sub I. So these steps and the work A to B is the interval over the path C. Over the path C. Oh. Not dx. And of course, you know how to calculate line. All right. What's the Work AB divided by Q. Q being the charge. Okay, but I understand this, we're gonna find that, make sure we know how this is connected to this, and, that was a little challenging. What's the definition of electric field? Didn't really get a good definition. It's not at first, it's supposed to be in a chart. So how is this related to this? Well, you gotta multiply the force per unit charge by the charge, which is Q. Same Q here as we divide by here, right? So that would be well, we could say that's a force per unit force over the charge times delta S. Electric field is force per unit charge. Okay. Let's see, integral E dot 3S. Right? Okay. Now, what do we call the work per unit charge? That's a definition of something important. All right. Now, these are the fundamental relations. This is what everything is built on. Okay. And you're probably going to do better on the exam if you're really clear on these relationships. And you can be clear on all this. But if you don't know this, and no offense, but you don't know what you're talking about, which means it's going to be more difficult to conceptualize and solve some of the problems that we've seen. Okay. So what I want to really advocate is that you go back to the, I'd start with the introductory problem sets. And if those don't work for you, they tend to work pretty well for those people. If they don't work for you, you go back to your chapter review. What are your basic definitions? What are your basic relationships? Because if you know those basic definitions and relationships, number one, you're less likely to not remember a formula that you need to remember. Okay. In other words, if you do understand them, you're more likely to understand what the formulas are telling you, which will give the formulas more meaning to it. Okay. So you understand this one thing, it's a kind of a new too. Now, the other thing is, and that's not difficult. You knew that 2 months ago. When we first started this, you have those relationships. You could reason things out in terms of the definitions, in terms of the units. That's another way to think about it. If you like to use units, well, what's the unit of electric field? Units per coulomb. I got to know what the units are. What's in force? Well, that's newtons. Okay, you got newtons per coulomb, newtons. How's that related? Well, you multiply the coulomb by the coulombs, you get newtons. So it's fine to think about it that way. You kind of maybe want to abstract it a little more to what's the definition of electric field? Okay, what's the units of meters per coulomb? So it must be force over charge. That force per unit charge. And then how do you get the force if you know the charge of the electric field? Well, same reasoning. You got to turn it around a little bit. And that's not a totally easy thing to do. Easy to lose track of it. Okay, you knew it when it was fresh. So okay. Okay, so Anyhow, there we have it. So let me just emphasize it. This is really important. Okay, and the other thing is, of course, if it's an electric field, it's a gradient. Electric field is a gradient, which means that the work between here and here doesn't depend on the path. As they depend, it's a conservative field. Okay, so let's just make sure we understand that electric field F is a potential function, QF is a potential energy function for a given charge Q. Just like your gravitational field is what you multiply by the mass to get the gravitational force. Concept that hopefully can help to some extent. So then there's an analogy there. So that voltage, AB, voltage between 2 points is well defined. If he is conservative. Yes, have that opinion. Okay. Other things you really need to understand about the electric field, that's the foundation. And if you understand that foundation well, then a lot of other things start to really make sense. Okay. Now, if you've got a circuit. Then typically you've got a wire. Someone's going to say this is not full state, it's a wire with charge barrier. Got a length L. Let this be point A. Let this be point B. You know, it's not really. I don't know. There it is here. Capital A and capital B, I use lowercase here. A lot of times you have to enter the much from A to B. It's little a and little b. Anyhow, okay, so we have a voltage AB. measuring the voltage. Okay. Now, if it's a uniform wire and homogeneous, equal numbers of charge carriers and same material, you know, distributed uniformly throughout. Okay. So, can you tell me what the electric field in that wire is? What's the electric field in the wire? Well, in the first place, it's got to be uniform. Because if it's not uniform, charges are going to rearrange themselves to make it uniform. Okay, you can't have a net accumulation of charge any place. And if it's a uniform wire, the electric field has to be the same. Okay. So, electric field in the wire, how do we, first of all, it's got to be uniform. I'm looking for the reasons we should understand that. Okay. Uniform. Okay, well. A lot of times easier to reason by units than it is to reason by abstract relationships. Okay. But we're going to reason it out both ways by units. PABs and joules per coulomb. And we can reason by definition, if you know that voltage is in joules per coulomb, then it doesn't take much to say that voltage is the word for even charge, which we should understand, but we can understand this really well. Work from ABs, of course, times the distance. Well, okay. And of course, that goes back to the definition of work. Reason by definition, yeah, work AB. Actually, it's the integral of F dot ds. But F and ds are in the same direction. By sigma for your electric field has to be in the direction of the wire, this way or this way, depending how your voltage works. So you don't really need the dot product. And you don't really need the interval, because it's going to be uniform. In this case, it's F delta X. Okay. Then the electric field then I'm kind of getting, I don't know how to do it. But that's okay, we know what work is. Right. Then joules is our work into the force factor. Okay. Electric field is in newtons per coulomb. Joules is newtons times meters. He's in newton meters per coulomb. And we can think about it. I think it just comes down to the voltage is joules per coulomb, electric field newtons per coulomb. You better divide the joules by the meters. Okay. And it's in newtons per coulomb, which is in newton meters per coulomb divided by meters. Is joules divided by meters. Well, playing around with this. The electric field is going to be a force on the left. The force is the work done divided by delta S. Your electric field is force over charge. Voltage AB is work over charge. Okay. That comes out your voltage by L. Okay, now I'm just thinking about different ways to make this clear, and I think I've been pretty helpful. I'll mention that. You knew when we started this that you divide your voltage by your distance to get electric field. Okay, that's what it comes down to. We're going to say E times L. In terms of this. Here's your voltage. You just come right down to this. Reason it out in terms of units. Reason it out by definitions. Since this equals this. In this case, E is constant. In this case, it's E times L. Come back to this. You get this. Let's just take the idea, okay, that E. And they're dealing with the nichrome wire with a lot of that. Go back and look at your data. Okay. That's what we discussed. So what happens is it will charge? What's the acceleration of the charge? We know the charge and the mass. How do we get the acceleration? What happens to the charge in a wire when it gets accelerated? We talked quite a bit about this. We should talk about it for a second. We'll talk about this, but you really want to have a picture of what's happening to those electrons. Okay, first place, there's no electric field. They don't just sit there. We're talking about the free electrons in conduction, and electrons are free to move around, okay? So it's not an absolute zero. There's thermal energy. Okay, so translational kinetic energy, so I'll put the plants in there. Okay. One kinetic energy is 3/2 kT. Okay, they bounce around, essentially colliding with atoms, quantum mechanical wave thing, and they bounce around off of each other, off of the atoms. You can think of it that way, unless you're down to the quantum level. Yeah, but you gotta go into chip design. Transistors are getting down almost to the nanometer size. 1,000 atoms in the side. Okay. And that all becomes very quantum. Okay, but that helps. It bounce around. Just looking at the picture that's sufficient to understand what happens in the wires that we've dealt with in lab. Okay. Go to the quantum mechanical level. Okay, they bounce around and they get accelerated for a little while. But they have an unimaginable number of collisions every second. So they don't get accelerated for long until they bump into something. Okay. No time for them to change velocity very much. If the velocity is corrected, in the direction of the force. They all tend to drift. What's the picture you want to have of production? And there's more to it. Okay, then, and we don't have time to go over it all. You got a thick wire, you got more charge carriers per unit length. Drifting at the velocity they drift at, but there's more charge carriers drifting, so you have a bigger current. Okay. And it goes into conductance and conductivity and all the stuff that you're gonna want to review. Okay,